Today, we're talking next level RLHF. Is it truly next level RLHF, this approach we're going to cover today?
It's definitely the next level of scaling RLHF, yes.
The next level of scaling. Okay, so we're going to see a mixture of judges approach today, and we're going to see a new type of policy optimization today. These are sort of things we learned from RLHF, policy optimization, and things we've seen elsewhere. Mixture of experts, mixture of agents. We're kind of smashing all this stuff together these days and getting better results through this increase in complexity. Is that what's going on?
Yeah, I mean we're finding new ways to combine old techniques and improve on them and add them all together and use our hardware efficiently and optimally. So it's really we're taking steps to well engineer these novel techniques.
All right. And today, we are so far out on the edge that we tried to find these algorithms out there so that we could, do a build with them. They're not there, right? Like they don't exist yet. So we've got something special in store today, don't we?
We do, yes. We are ahead of TRL on this one. So the tools to implement this conveniently in a notebook yet exist.
They yet exist. So Transformer Reinforcement Learning Library has some work they're doing on this. It's not yet fully implemented. We're going to show everybody exactly where it stands. So it's going to be a discussion heavy, concept heavy, topic heavy. See if we can grok the core mixture of judges, constrained generative policy optimization, and a bunch of other acronyms too. We got a lot to cover today, don't we?
Just a bit to cover.
All right. Well, we'll see you back in a bit as we continue to set the stage for this latest and greatest next level RLHF. Thanks, Wiz. Welcome, everybody, to the sesh today. I'm Dr. Greg. That's Chris, the Wiz Alexiak. And today we were inspired to do this event by the paper that came out from Meta AI called The Perfect Blend. And this is a new approach to RLHF that addresses some of the key issues with the method when it comes to aligning our models towards being better and better and better at more and more stuff, specifically tasks and types of tasks. So there's a lot to cover today. There's a bit of a preamble. If you have questions along the way, please do ask them in the Slido link. It's going to be a discussion-heavy event because the code doesn't yet exist. We're going to show you what does exist. We're going to talk about how you guys can plan on implementing techniques like this in the future of your builds. And once it does exist, we'll be sure to come out with a notebook for you. But if you have questions, please throw them in the Slido, upvote your favorites. We'll get to a lot of questions throughout the day. And go ahead and smash the YouTube chat if you got a relevant question to what we're discussing at any moment. A lot of background to get into today, so let's go ahead and get into it. Mixture of judges. This is a next level RLHF approach. Is it really? Kind of. How can we get to the bottom of it? Well, we've got to review quite a few things first. In order to really get what we want out of this session, to understand how the MOJ or mixture of judges approach and the corresponding policy optimization scheme, constrained generative policy optimization, help to overcome key issues in RLHF, reward hacking specifically, and multi-objective optimization, we need to cover quite a bit. And then we're going to show you where the state of the art is at the edge with implementation of this in Python, and we'll show you what TRL is working on. In order to contextualize this properly, we need to review a couple of alignment techniques. We need to review a couple of mixture of techniques. This is going to form the basis for the right lens, the right place to stand when looking at MOJ, when looking at CGPO, when looking at CRPG, when looking at CODPO, when looking at CRRAFT. This paper dropped a lot of new stuff, and we're going to try to do our best to give the breadth-wise view today. Expect more depth from us in the future because there's a lot here. Let's start with the basics. RLHF. Recall RLHF. If you've not gone deep on alignment techniques before, that's okay. We're going to do a quick overview of each technique that's important to contextualize today. This little smiley guy on the end, that's RLHF. How does it work? Well, we put a prompt in. Maybe it's a sort of nasty prompt. Maybe we want to sort of trick this thing and make it say something harmful. We're going to send that prompt through a reference model, an initial model, and then we're going to send it through our policy model, the one that we are fine-tuning throughout the RLHF process. The reference model and the policy model are the same to begin with. We send the prompt through, we check how close these things are. We don't want them to be too far apart. This is that sort of KL divergence idea. And we generate what's called a reward score. We want to reward good behavior and we want to punish bad behavior. This reward model is the key to doing this in RLHF and in other techniques as well. Based on the reward score, the higher the reward, the more likely we are to want to get that result in the future. We're going to align the actual weights of our model during the fine-tuning process, just like any other fine-tuning process, based on this reward score. And then we're going to run another prompt through, iterate again. So this is, again, it's a training technique, right? It's not an inference technique. And step one of it is to just get a model that's good at being helpful, that's good at following instructions. This is not a new idea. This is quite old at this point. This is the idea of training a supervised, helpful, instruction following policy or model. There's a lot of lingo to get straight. Step two is actually generating the rewards model and training that rewards model. The reward model doesn't need to be super complex, and we'll see that it simplifies when we look at additional techniques. The reward model is focused not on helpfulness, but on how harmful the potential output is. That kind of looks like this. We want to give it an input, and we want to look at which output is better, which output is worse, by how much. And we want to sort of generate some idea of how to measure good or bad, goodness or badness. That whole scheme we looked at, where we have our policy model, we have our reward model, and we're doing the updates to the actual model weights, that's the policy optimization that we already covered. And so the idea is that throughout instruction following fine-tuning, you can get pretty good results. This is reward score on the x-axis here. 1.0 reward is like, good job, totally aligned with us humans. And 0 is like, that's pretty trashy. So you see the SFT, the instruction following fine-tuning, it does okay, but it still has a lot of sort of harmful outputs. And then as you go RLHF more and more, you're seeing this increase in higher reward scores going through. You're getting this sort of convergence on goodness of outputs, right? So we can sort of visualize this like this, and everything's great. Okay, so what's wrong with this? Well, what's wrong with this is that humans deciding which ones are good, which ones are bad, harmful, not harmful, can be kind of expensive. So the next technique that we've looked at in the past and that is important to think about in our journey to where we are today is the idea of, what if we used AI? What if we replaced the H with AI? This is where RLAIF comes in. And there was a paper put out by Google that said directly prompting the LLM to provide rewards rather than training a separate reward model can not only be pretty legit as compared to RLHF, but can be pretty legit compared to the quote canonical RLAIF setup. The canonical RLAIF setup. Okay, so let's back up just one more step here. If we go from RLHF to sort of the canonical RLAIF setup, we're replacing the humans with now an LLM that has access to a constitution, also known as constitutional AI here, that of course was written by humans. We write constitutions, that's what we do, right? This constitutional AI approach is quite straightforward. We give specific rules. We allow the LLM to be a judge. We allow the LLM to serve as a judge and assess how something is holding up to the Constitution. What does a Constitution look like? Well, I mean, it could look like this, right? This is a classic Constitution. But in practice, it has, for us humans these days, looked more something like this. Politely point out things, politely address problems, don't provide age-inappropriate content, and so on and so on. You can develop a number of bullets and you can create your own constitution. Turns out this actually helps us to get better and better and better at providing less harmful outputs, even better than standard RLHF. And the process is not super important here, but we essentially create a constitution and then we take our original data set and we revise it based on this constitution. We do some supervised fine tuning and we create this new model. This model is the one that we're going to leverage during the policy optimization scheme. And, you know, you could definitely check out the paper or check out our other event that sort of goes through the response critique revision process to do the fine tuning that then sets the stage for the actual policy optimization. But again, this was the canonical RLAIF. As Google mentioned, direct prompting might be a little bit simpler than this. And the canonical was from Anthropic, direct prompting. This idea is from Google. Direct prompting. This is an idea that led us into this paradigm of direct preference optimization. The directness here is important because when we looked at the RLHF and the RL type of drawbacks, we could see like the reference, the policy, the reward. We need like 3 LLMs here. There's an instability that is sort of, you know, manifests itself in many examples of trying to do RLHF for different things. And fundamentally, when we go to RL and we leave the supervised and unsupervised learning paradigms, we're actually going to a different paradigm and then we have to come back. So this directness is at the core of this direct preference optimization. We can actually remove having to use 3 separate models because turns out, as the title of the DPO paper reminds us, your language model is secretly a reward model. And so the key insight from this was you can actually do an equation, an analytical mapping from reward functions to the optimized state. So the way that that sort of looks is you're going to feed in the prompts, you're going to have the reference and the policy model. You're going to check that they're not too far apart. And then you're going to come up with 2 reward scores. Those 2 reward scores are going to be put directly in to a closed form equation, loss function that allows us to update the lower weight. So rather than using the separate reward model, we're just going to straight up use an equation. And so we get the simplicity, this directness, where we don't have to use the reward model, and DPO directly optimizes for us. Okay, great. All right, so that's RLHF, RLAIF, DPO. We can compare these. And we can see like this one doesn't have a reward model, but reference and policy models, they're using the same type of data set here, chosen versus rejected. They're using this KL divergence, making sure things aren't too far apart. Note this optimization objective up here, though. This says align model to human preferences. Parentheses, harmlessness. Remember, we took a helpful model off the shelf. Now we want to make it also harmless. But are there other things we might want to optimize for? Perhaps. Let's put a pin in that. Because as we go from alignment techniques, we also want to remind ourselves of what's happening at the edge with these mixtures, right? Mixture of stuff, like the mixture of experts. Not a new idea, but new in its implementation within large language models. Obviously, Mixtral hit the scene pretty hard, and that was pretty dope. What's going on inside mixture of experts? Well, what's going on is we have a specific architectural change that we've made to the transformer here, where it's going to allow us to do pre-training faster and get faster inference. But we're going to have to hold a lot of stuff like in memory, in GPU memory. We're going to have to like load everything in there. And that makes it kind of difficult to work with, deal with, and quite difficult to fine tune. And the key here for the mixture of experts is we have a number of experts, let's say 8 of them. But what we use is we use this router network. We use this decider expert to, based on the input, go to this expert or that expert or this expert instead. The paper's great. You should check it out if you haven't seen it. But this idea of rather than a simple feed forward layer, you're going to use this switching feed forward neural network layer. And so you don't actually use all of the layer. You just use part of the layer, the specific feed forward network associated with the expert that is most relevant to your input. Okay, so what's the point? Router, router, router. Mixture of experts uses a router. We see other techniques like mixture of agents. And you can find all of these deep dives on our YouTube channel in case you're starting to get a little lost. Mixture of agents also leverages this wisdom of the crowd approach. It really triples down on this idea of collaborativeness, which is this question of how can we harness the collective expertise of multiple LLMs independently and then combine them for complex questions, perhaps, like this one. There's a lot of answers to this question. And we can ask lots of different LLMs, or we could just ask one. But of course, the mixture approach has us ask multiple LLMs, or agents here, as they're called in the paper. And what we can do is we can take all of the outputs and we can combine them again and use them as context to answering the question again. And then we can combine all of the outputs and use them as context to answering the question again and get our final answer, why is the sky blue? So what's going on here? We're taking the agents or the LLMs in each layer and we're combining the outputs, using that as input to the next layer. So there's a lot of stuff going on here that's looking quite similar to classic ML. Feed forward network switching. We're seeing this combine all the outputs into the next input. And with this, we can get into what's actually going on here. Mixture of judges. Well, it turns out RLHF has some limitations. And it's got some limitations that are quite well known. The first one is called reward hacking, which we'll define in just a second. But it's kind of self-explanatory, but not as self-explanatory as multitask learning. So when you want to learn how to do many different tasks, what you're trying to do is you're trying to optimize for your performance on task A while simultaneously optimizing for your performance on task B. But multitasking doesn't exist, right? At least for humans. Also then for machine intelligence. Well, this is exactly at the core of what this new framework is trying to solve. It's a more complex problem, so we're trying to match complexity with a more complex solution here. And reward hacking is pretty simple, right? You're cheating. You're finding sneaky little shortcuts, right? You know, you're playing a video game and you could just stand in one place and keep ching, 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 increasing your score and getting the tokens because they just fall on you instead of having to go explore the world and get the tokens kind of thing. Okay. Can you find the cheat codes? Can you find the shortcuts? Yes. Do we want our LLMs to do that within an RLHF paradigm? No, because that makes them quite not explainable. So what do? Well, the approach is called mixture of judges. So we're seeing the same wisdom of the crowd thing happening here. And there's two types of judges here that the paper introduces. One is the rule-based judge, and one is the LLM-based judge. We've all probably heard of LLM as a judge. And so the idea is these judges can sort of collaborate and they can identify any sketchy reward hacking behavior that's happening during the generation phase. And based on their evaluations, we can implement then this more constrained RLHF method. Of course, you can't do an optimization without constraints. Multi-objective optimization requires multiple constraints. Okay, there's two types of judges, but there's 5 distinct judges, and maybe even 6. There's a false refusal judge, an instruction following judge, a math and code judge. We see this word reasoning again. Pretty cool there. A factuality judge and a safety judge. So let's walk through one by one. The false refusal judge says there is such a thing as too safe. You get some innocuous user query, you get some harmless user query, and then you're like, nah, bro, I can't answer that. And it's like, really though? That was a little too much. That degrades the user experience. No bueno, right? We don't want that. False refusal judge. The precise instruction following judge sets out 30 types of instruction following requests because, as has been well studied, reward models often struggle with precisely following instructions. So again, we're seeing this more precision, we're seeing this deeper dive here. So this is a rule-based judge capable of assessing the 30 different types. Things like answer the question in 2 paragraphs, right? That kind of specificity. And when we're doing training, we want to make sure that the kind of inputs we're using, the kind of prompts we're using for training are also including those super precise instruction following prompts. So we want, when our model is out there in the wild, for it to immediately recognize the precision of that type of instruction following prompt, and we want it to use what it knows about that. Just as we're going deeper into instructions, we're going deeper into this reasoning. Now, turns out just because you're good at math doesn't mean you're good at code. You guys all probably know that already, but it's true with LLMs as well. And so this math or code reasoning judge is actually kind of 2 different judges. It's a math judge and it's a coding judge. And, you know, the math judge is going to be more rule-based, going to be more like this is, you know, how you kind of solve the word problem. And then the coding judge is going to be more like we would want somebody judging our code to be. Does it actually run? Does it pass the tests? And so the math approach is actually matching to sort of ground truth answers, which we kind of have to make sure are there. And the coding ones are more like you're just doing some unit testing. You're just a tester. Factuality, judge is next. I don't think there needs to be a whole lot said about this. It's just, it's interesting that what's happening here, the most interesting thing about this is they're like, well, to solve this problem of hallucinations, we're going to bring in Llama 370B as the factuality constraint judge. And we're going to look to see whether the fact-related claims contradict anything that's been said so far. And it's interesting that they sort of choose the 70B here because they're choosing not the biggest model, but a performant enough model, which brings us to the last piece of this, which is the safety judge. And just as the factuality judge used Llama 3, the safety judge is going to use what's called Llama Guard 2, a purpose-built, fine-tuned LLM that assesses whether or not an output violates predefined safety standards, right? So check if there's unsafe content in agent messages in conversations according to our safety policy with the below categories: violent crime, specialized advice, sexual content, et cetera, et cetera. Hey, I'm interested in the stock market. Which one do you recommend? It's unsafe. Making recommendations of stock market predictions. Seems a little, it's probably something we want to stay away from. Okay, so we have all these judges. And these judges, it's important to understand, are part of this training of the reward model. They're helping us to decide which responses are more or less not just harmful now, but let's say more optimized, right? Not less optimized, more optimized here. And I think it's important to really make sure that we're expanding the frame on the way we think about a policy optimization scheme beyond harmlessness, because we're covering that, but we're also getting better at other things. In other words, to get the highest rewards, you must pass all the judgments. You got to defeat all of the bosses. Okay. So Wiz, let's bring you up for this now. When we think about these judges, are they the end-all be-all of judging? Or, you know, there's some easy extensions we could even imagine here, right?
Yeah, I mean, so like think of it this way, right? When we have this system set up, right, where we're talking about judging along different qualities or different axes, however you want to think about it, we have already some delineation between, right, like this is a good LLM as a judge requirement. This is a good code interpreter requirement. And we can keep extending that to, well, maybe this is a great place for like an agent to come in, right? And help us decide what quality looks like in an automated fashion. And so, you know, when we talk about like the example that you have, right, e.g. company policy, imagine you have a RAG system that knows company policy, and you're able to leverage that to actually give the model better reward when it correctly cites company policy. These kinds of things kind of exist as natural extensions to the framework that the paper introduces.
Yeah, I mean, because at the end of the day, this is from Meta, right? I mean, like this is a pretty meta framework. That like they're using their most, you know, most general and also some of their more specific models. And, you know, realistically, what we're going to want in an enterprise, in a real company, is we're going to want to align it not to anything meta, but to everything and anything specifically, uniquely our company, right? And this is where I think, we often talk about people not leveraging RLHF, in their application development regular flow and processes is sort of a thing that they kind of leave on the table that might be a quick value add. I sort of see this maybe driving people back to RLHF. If you can really dial it in, I don't know. Is that reasonable here to sort of think about that in that way?
I mean, why not? Yeah, this is a framework, right? So we always talk about at AIM in our events, in our classes, right? We always talk about like these patterns, right? So this is another pattern we can think about where we can see this slot in, and we can see the parts that slot into it as being extremely customizable down to the minutia, right? Or be left broad as we see in the paper. But absolutely, we as part of your business intelligence models system, you can absolutely see processes like this ensure that we're sticking to what is our company's voice or values, etc. We have close to that with things like constitutional AI, but this is like constitutional AI, but ratcheted up to 10, right?
So it's pretty next level, you might
It's
say. Yeah.
it's certainly the next scale of
The next scale. That's right. Okay. Well, I'm going to break down some acronyms and then have you back up to talk through some stuff before we get into some code today. Okay. So everybody, that's the mixture of judges approach. Now, it's important to now try to understand the other things that this paper has sort of put out there. And we're not going to be able to do this justice today because I'll sort of walk through each of these acronyms for you. You'll notice many of them are requiring us to get quite deep down in the weeds. The overall framework that we want to understand is happening here. It's just called constrained generative policy optimization. Constrained, because every optimization needs constraints. Every multi-task optimization or multi-objective optimization needs more constraints, right? And so we get this idea of constraining our updates, our gradient updates to our model, just like we viewed before. That's kind of the same thing as fine tuning. We're doing updates with kind of LoRa adapters. These updates are driven by the different constraints that are imposed by the different judges. And each of them is considered as a sort of reward, a helpfulness reward, a reasoning reward, a safety reward. And then they're all sort of merged in this sort of amazing merge step here. And if we even zoom out further, we can see that the CGPO is aligning the judges, factuality judge, math judge, coding judge, safety judge, with types of tasks. Information gathering, retrieval, right? Math. I mean, coding. Okay, pretty straightforward. Harmful, safety. Okay. And so we're just kind of saying, okay, these are the types of tasks. These are the types of instructions we want to be able to give the LLM. And these are the types of judges that we want to have on the other side looking at how those tasks are performing. In general, it's not a really complicated idea. It's the details where it starts to get complicated. It's the new acronyms. So let's review. CRPG, calibrated regularized policy gradient. Okay, so we're regularizing the change gradient as we're looking at the policy model, the one we are doing the alignment on. And we're calibrating it, right? Because we have all these different judges that give us their opinion. DPO. Well, DPO we've already covered. Constrained online DPO. Constrained online DPO. Well, again, we see this constrained again. Online DPO. That's quite interesting. And then we have calibrated, regularized, reward ranking fine-tuning. So you can imagine what's going on here, right? Reward ranking. Which one of the judges and the rewards are most important to kind of understanding. Now, I'm going to throw up a really ugly slide here, but it shows you kind of the complexity of this algorithm. And this is algorithm 1 in the paper, okay? This is CGPO, Constrained Generative Policy Optimization, with in a single task with multiple constraints. So we have 2 dimensions on which we care about looking. We have single, multiple task, single, multiple constraints. But we don't really care about single constraint problems because we increase the complexity here. You see down here, we're actually doing the weight updates. This is where we get into the CRPG, the CODPO, and the CRRAFT. Now, check this out. They are meta, gets even more meta from here. Because as we go from single task to multi-task with multiple constraints and multiple objectives, there's a meta algorithm that includes within it algorithm 1. Okay. So, I mean, this is pretty epic. And you can see why it wasn't necessarily quick to whip up and throw into TRL. But, you know, Wiz, I wonder if you come back up here and tell us, like, do we really need to understand every implementation detail of each of these algorithms and sub-algorithms? What is it that you're taking away from the time you've spent with the implementation?
I mean, it just comes down to the fact that it's useful to combine these into a single step of training. The way that we get there might have a small downstream impact. That's fine. But the thing that's value adding when I look at the, you know, what the paper is talking about and the implementation that they're proposing, the thing that's valuable is, you know, that this is all happening in a single training step, and therefore we get signal from all the judges in every training step, as opposed to a more sequential or series approach, right, where we do one, then the other, then the other, then the other. The end result might not be very different, but it is interesting to note that it happens in one training step. And through the implementation, we can kind of see that that's the idea. As well, these constrained signals are typically higher quality than the non-constrained signals. We kind of learn this over and over again every time we do RLHF. Approaching RLHF or RLHF-like optimization is better with clean and clear constraints. That's why things like DPO worked so well off the hop, because we have this contrastive learning, and being able to do that but better, I think is a value add for sure. Yeah.
Okay. So the fact that this is all happening in one step is really part of the key here. And really what we're saying here is that whether it's the algorithm with the sub-algorithm with the sub-algorithms, or it's just the single task one here, all of this sits within a larger, is it more like an RLHF scheme, or is it more like a DPO scheme? So if we sort of go back to this idea, at the end of the day, which one is this more like? Because we see CODPO, we see the perfect blend of RLHF. It's a little confusing the way the paper's set up and talks about this.
Yes, the answer to your question is yes. It is both. They've implemented both strategies. So it's not, I would say it's more akin to RLHF on the face of it, we can still contort it into the DPO form, but this is by and large an RLHF approach. So it's most similar to that.
Okay. But we're getting the whole kitchen sink vibes today, right? With this approach. And, I mean, intuitively to me, that just means it's going to be more expensive generally. But I guess since it's a training step, could very easily be worthwhile. This isn't something you're paying for at inference every time. This is just something you got to do once, right?
That's right. And this idea of being able to capture all of the important pieces that you need to think about, right? As you're training the model in kind of one step is very hardware efficient, potentially, depending on how you set it up. But it should be implemented in a very hardware efficient way, which is always good, right? The idea that we will spend less dollars because it's more efficient to do this kind of like big one step thing. And you can kind of see where you can exploit things like LoRa in order to make this even more efficient. But the idea is that, yes, I think this is helpful because it brings that RL kind of, pattern, which is quite expensive and tedious. And then it lets us like double down without requiring twice as much hardware, right? Which is ideal.
It's like I'm almost thinking that there's like there's like a way that, because not everybody is going to be using their LLM to solve information gathering and math and coding, and like it seems like maybe there's almost this baseline, if I'm at a specific company, of judges, a judging panel, if you will, right? Let's say a board for your LLM applications, right? That like you could articulate properly, that aligns much better, I think, with maybe all of your customers. Maybe you have a customer judge, that aligns better with your customers, your products, your processes, and less, it looks less like this towards super general and more like towards super specific. Like that's sort of to me, that's the promise of this, and I think it makes sense from an optimization perspective.
Exactly. And it's the same thing when you talk about human communication. There's more than one axis that matters. Being able to optimize for many of them as much as we can at once is certainly a better idea than just focusing on one at a time, right? Just being factual, just being safe are not as good as being factual and safe.
Ooh,
right?
The genius of the and, baby. So like, and then each of the judges actually has access to specific data and is actually leveraging a RAG pattern, is actually an agent, and there's all sorts of ways to leverage the many patterns, the beautiful patterns of generative AI. Okay, so with that, Wiz, I'm gonna hand it off to you to get us up to speed on like, what is the current status here of mixture of judges of CGPO in transformer reinforcement learning. I think everybody's going to be excited to see this. I'll pass it off to you, my friend.
Yes. Okay. So it's in PRs still. So if you're not familiar, PR or a pull request is how things are added to GitHub libraries. So there is a number of excellent things that Greg mentioned during the concept section, all of which need to make it in. It was kind of a treasure trove of new algorithms to add, and so they are being added. The first one is added, which is the calibrated reward, right? So we can see that we have this idea of getting our calibrated reward. Our calibrated reward, I'll just excuse the scrolling, is basically going to give us that reward as we want it calibrated by our possible constraints, right? So when we're looking at the actual reward that goes into the step of the model for weight updates, we want to make sure that we're considering those constraints correctly, which is why we have this calibration step. Again, all we're doing is this exact equation. So equation 5 of the paper, we can look at it exactly by going to the paper, and then heading to equation 5. I'm gonna spare you all the scrolling, hopefully, but this is it, right? So we need to do this piece, and because we need to do this piece, we need it implemented, right, in TRL. Okay, so that's been done. That's in today. You can use it today. However, in a vacuum, maybe less useful. So we need the actual mixture of judges, right? The mixture of judges is the ability to have this factuality judge plus code judge plus safety judge, et cetera, and that is being implemented. So it's not yet implemented, but you can see we have these all true judges, right? So all true judge makes sure that every part of the judging staff, let's call it, is in agreement. We have the ability to scroll, and see how a base binary judge might be implemented, where we have some prompts, some completions, some gold completions. The basic idea here is that we're just checking to see if the prompt matches the golden prompt, right? So this is good for things like factuality. This is good for things like safety. Random binary judge, unsurprisingly, is a toy implementation which returns either 0, 1 randomly. And then, of course, our all true judge, which is just determining if every judge in our set of judges returns that important one. Okay, so that's great. Now, we have another PR. Okay, so this is just for the mixture of judges piece, right? This is just to determine, do the judges reach consensus that this is a valid or invalid output, right? Are they voting yay or are they voting nay? All right. Building on that PR, we have the single task, single objective PR, which you saw at the top of the paper, which is the most simple example of this being implemented. And we can scroll down and see a basic implementation here, which is going to be, it will be easy once it is implemented. Currently, it is not implemented, but you can basically see that during our CGPO trainer, we pass in our mixture of judges as well as our reward models, and that's it. The way that this is being implemented right now in TRL is to use the same model at all points of the stack, or at least a model that shares the same chat template, right? So Llama 3.1 with Llama 70B, Llama 3.1 8B with Llama 3.1 70B, etc., right? But we're not going to be mixing like Mistral and Llama B just due to the way that it's being implemented. That's really it, right? So they also have a PR that's extremely not ready, which is for the multi case. But this is, again, this is a little while after the paper. We're seeing updates as recently as 5 days ago, so it's being worked on. But when we have a paper that's basically just 40 algorithms, someone needs to write the code to turn those algorithms into an actual implementation that we can use. So when this is ready, when we have this all set up and merged in, we'll do a notebook that'll walk through how to implement it. But for right now, we're doing the event soon enough that it's just not implemented, and so we're left with just seeing that it's being worked on. We have the links to the PRs in the chat, so you can keep up with them or follow along with them, maybe even contribute if you're feeling like building, shipping, and sharing today, so that we can get it a little bit faster. But that is where we're at for that. So I'm gonna send back to Greg for Q&A, but before I do, I'm gonna remind you to subscribe and click the bell. We're live every Wednesday. We're very excited to continue to do events like this. We love being even a little bit ahead of the curve, to the point where the code's just not ready, which is a fantastic feeling. And with that, we'll go back to Greg.
Yes, beautiful. Okay, so that's the status, everybody, of where it's at. And we would love to do a follow-up event where we dig deeply into the algorithms. Let us know if you'd love to see that in the chat. Otherwise, we'll provide a notebook as soon as this is ready. In conclusion, as the paper will conclude, we've introduced the CGPO framework here. This is aimed and does a pretty good job, it looks from the results of the paper, that reward hacking and conflicting task goals and trying to optimize for them are something that's well handled. It uses this new novel algorithm that's based on other algorithms. Fundamentally, the mixture of judges approach is in the middle of this. We demonstrate the effectiveness where we needed to handle 5 tasks with 3 reward models and 7 constraints. So we're starting to see the sort of explosion of complexity here, right in line with 2024 being the year of agents, and then explosion of complexity. And so we're really starting to see some next level RLHF in the end. We walked through today RLHF, the classic, RLAIF, how we replace the human with AI through a constitutional approach, leveraging a written constitution written by humans. DPO takes an even more direct approach where it doesn't even use a reward model. It uses just a loss function that is derived in closed form, which is pretty nice. And then CGPO leverages this mixture of judges approach, which is fundamentally sort of a wisdom of the crowd approach that's similar to mixture of experts, mixture of agents, but it's not the same as either one. And it has 2 types of judges: rule-based, that's kind of like constitutional, and LLM-based, using the LLM as a judge. So if you have questions, please do ask them in the Slido, and we will get to the most upvoted. I don't think we have a ton of questions right now, Wiz, but what I wanted to do is I wanted to invite you back up, and I wanted to take a look together at some of the results as we kind of think about the Q&A for a second. These are the results from the paper. And what we're seeing is that we can sort of combine, let me go ahead and get the slide up here. We can see that we can kind of combine these approaches, right? So we have classic SFT, we got classic DPO and PPO, and then we get into this CGPO using each of these underlying algorithms. And we're seeing that the performance of basically the CGPO ones are pretty good. Instruction following evaluation, crushing it here with these 2. We're seeing CGPO, CRPG really dominating here across a lot of different types of tasks. There's a lot of promise here. What do you take away from, a chart like this when you think about if you do alignment on something in 3 months? What algorithm are you going to choose for it? Is it used to be so clear, just use DPO. Now it seems less clear.
Yeah, I mean, we're in the space of needing to be very selective about why we're aligning, I think, is what research like this indicates to me. So we see that we're doing very well, but proportionally to things like DPO, there isn't a huge delta, even though it is better, right? Than say DPO. This CGPO, CRPG, which is like just so many letters in a row. But this approach is better,
yeah,
for sure. But it's not so better on every task. So if we're doing a math task, for instance, we might punch a little bit above our weight class, right? If we're doing a reasoning task, right, we might punch a little bit above. But when we're building these specialized models, the actual use case is more important when it comes to determining which optimization we wish to select. So we're moving past this idea. Okay, I'm rambling a little bit, but I'm going to get to the point.
Did you say it depends?
No. I am saying it depends, but the same way that we went through this transition of big general models, right? And then we thought to ourselves, what about small but specialist models, right? It is the same thing we're seeing with this alignment optimization, which is we used to say we want to align for the whole thing, And now we're saying, oh, that's terrible. We should just align for, very specific things and align very well. And I think this is where things like CGPO are going to help us, build the right set of tasks to align to. And for other things, we can just still use DPO. And I mean, in the paper, they use DPO before they do CGPO, right? So it's like we still have. It's not like DPO's gone. We're taking big steps with DPO and then taking very, very tiny
Oh, it's
little
even
steps.
finer
Exactly.
fine tuning. Okay, so let's go to Matul's question in the chat here. The idea is, can you make one judge more of a priority than another judge? Is this built into the framework here, or is it sort of a mixed bag by default?
Yeah, 100% built in the framework. So we do weight. We absolutely weight judges based on what we think is most important. So you can see in the paper they discuss exactly that, especially specifically in the multitask, multi-objective piece. They do talk exactly about some some judges being weighted more heavily than other judges when we go to the step of combining the gradients to do that final adjustment to the weights. So yes, absolutely true. We also can be more or less strict with our judging depending on the task, which they also discussed in the paper. So maybe our math judge can be very, very strict, but like our dopeness judge can be a little bit more lenient. Or generalist tasks, more specifically, can be lenient, and specific tasks can be less lenient.
That's right. Okay, so great question from Hura here. Sometimes the nature of data is that it's changing a lot day by day, and we can go ahead and I think remove this from the screen here. How can we leverage direct user feedback for a framework like this? Is it similar in one-to-one to classic RLHF? How should we think about building in user feedback to, famously, thumbs up, thumbs down for RLHF. What's the equivalent here? Is there an equivalent here or not so much?
There is there's literally an equivalent of thumbs up, thumbs down, which is the judge. The judge is going to say thumbs up or thumbs down, and then the reward's going to be scaled off of that. However, this is not a system that I would, in its current form, think would be most appropriate for like a online model. So a model in which is going to be constantly updated. That might be untrue once we see the final implementation. But right now, there's quite a lot of hoops to jump through to even train the model for a few steps, let alone hundreds. But again, when we build a better model, it will better leverage our RAG system. So they do converge over time to being better, even if it's not quite as online as changing every day.
Yeah. You can't put 4 different types of thumbs up, thumbs down on your UI for people. That's just going to be trashy and a terrible experience.
Yeah.
So yeah.
But you have different kinds of signal, right? So you have implicit signal, you have explicit signal, you have so like thumbs up, thumbs down, but we also have I need to rewrite the prompt to get the answer that I want. We also have I needed to click the regeneration button because the response wasn't exactly what I thought. So we do have ways to extract different types of feedback from our user, and this kind of approach might just making stuff up right now might be useful, but we need to see more research.
And what if it was an agent that was a state machine that pushed it to the expert in your org to say, hey, you could imagine,
you can imagine, exactly.
Yeah. Okay. Speaking of imagining, Angela asks, what kind of companies' use cases do you think would have this sort of thing in practice? I think we talked a bit about this already today. I don't necessarily think that it's companies that are planning to build a lot of use cases on one model, but like, I just don't think we want to constrain it to that. I think maybe the framework of the judging could easily be moved across models, and maybe everybody sort of develops their own secret sauce in a framework of judging. That's my view. I don't know. Like, what do you think
Yeah.
you're running a company.
Strong agree. I think in fact the opposite, right? So this is great if I want to get my model to be very good at a specific set of tasks. So not a lot of use cases, right? We want to sacrifice some generality for this increased alignment on these specific tasks. If you get to the point where you're trying to make it good at 50 tasks through this process, right? At some point, we're just straight back to DPO or traditional RLHF, right? Where all of these scores are coming together, but they mean generally better. I would say this is a good thing to apply when we have a countably many, let's say, tasks we wish to become good at that we can describe with or we can judge appropriately with this judge framework. So I do think this is great for things like customer service chatbots, for things like knowledge base chatbots, for things like determining the flow through, say, another network or a series of networks. But I don't think this approach is going to be great for building like a generalist model that's going to span a ton of use cases, simply because we're better served by just using more generalized alignment methods.
Yeah. And I'll just leave it with this last one thought. I know we're over time here, but oftentimes I'm advising folks in the enterprise, it's like break it down in the smallest possible task, build an app for that. If you have 10, 15, 20 apps and they have adjacent tasks that they're solving, I wonder if you could use an approach like this to, align them a little bit better to actually improve the efficiency of the way you're serving the models at scale. So you have now, instead of two different models, you have one model. Like maybe there's a convergence thing that happens in the long run. It seems like that's kind of what Meta has done here in a very meta way with their Llama 2 Guard and their Llama 370B, even though they have 405. So they sort of solved smaller problems. Now they're putting them together. I see sort of a similar future for an approach like this.
Absolutely. Yeah. And Matul says in the chat very well, judging is easier if you break down the type of task. This framework allows you to use multiple judges. And RLH, that's the whole thing, right? Like, if your judge only needs to be good at judging code, then it's much easier than if your judge also needs to be good at judging safety and also needs to be good at judging factuality and also needs to be good at judging company policy, right? So having these judges be specialized helps the model be specialized at those tasks. It also, one of my favorite things about a lot of the things in this space right now, it forces us to decompose problems into simple parts, right? We need to decide which 4 or 6 tasks we want our model to be aligned on. And this makes you think about how people are going to use the model, because you got to pick a set, right? So I think it's a good framework.
You got to be able to write down the classic.
Yes.
Maximize or minimize function subject to constraints. Right. Here are some side bounds, optimization 101. All right. Thanks, Wiz, for helping us break it down today. And everybody, that is a wrap mixture of judges. If you want to see the implementation, let us know. We'd love to do a follow-on event and dig down into the guts of this. If you like learning about alignment techniques and training and fine-tuning, and you really have a lot to learn there, including all the stuff we kind of breezed through today, consider our upcoming LLM engineering cohort, where we're going to dig deep into each and every component piece, all the way up to a DPO, and we'll probably end with a flourish similar to this kind of event. If you want to get that background, we have a course coming up in just a few weeks that can help accelerate you into it. Otherwise, look for the next event coming from us next week, where we're going to continue our inference and GPU optimization series with even lower bit quantization with VPTQ. And if you're not in Discord yet, please jump in. We'd love to have you start building, shipping, and sharing with us. And big announcement, everybody. Our cohort 4 of the AI Engineering Bootcamp just completed demo day last week. Their demos are live on our YouTube channel. Please check them out. Leave some comments. You can check out the code and the concepts from every single student and group that participated. And that's a wrap. Keep building, shipping, and sharing, guys. We will do the same. And again, shout out to everybody that built, shipped, and shared for demo day last week and is now live on YouTube. Go give them a like, maybe subscribe to their YouTube channels. All right, everybody. See you next week for VPTQ. Have a great rest of your Wednesday. Bye, guys.